Hi everyone, I am Amir Reza. This semester, I took a seminar called Fantastic Datasets and Where to Find Them. We have spent the last few months learning that a dataset is more than just a folder of numbers. It is a story waiting to be told. So today is going to be different. We are not going to build a neural network, and we are not writing complex code. Instead, we are going to dissect a legend, the Case Western Reserve University Bearing Dataset. This data was collected around the year 2000. Can you imagine? Windows 98 had just come out. Yet the work they did back then became a pioneer in the industry. In this video, I am going to walk you through four things: the why, the how, the what, and the verdict. First, let's answer a philosophical question. Why? Why did researchers spend time and money creating this? To answer that, we need to agree on what a bearing actually is. If you know, great. If not, here is the simple definition. It is the component that lets things rotate smoothly. Imagine a bicycle. If the wheel connected directly to the metal frame, you would have massive friction. It would grind, get hot, and eventually lock up. A bearing sits in the middle to prevent that. The most famous type is the ball bearing. It has three main parts: the inner race, the metal balls, and the outer race. Now, let's look at the stakes. Imagine you own a railway company. You have a massive train full of passengers. Suddenly, one single bearing out of thousands fails. The train stops. Best case scenario, you replace the part. Worst case, that broken bearing destroys the motor shaft and gears, landing you with a massive repair bill. Your passengers are late, they are angry, and you lose money. All because of one small metal ball. So, you need a plan. You have two options. Option 1 is preventive maintenance. You change every bearing every 6 months, whether it needs it or not. It is safe, but it is wasteful. Imagine if hundreds of those bearings could have lasted for another year. You are throwing money away. Option 2 is predictive maintenance. This is the smart way. What if you knew exactly when a bearing was going to break? You could fix it just in time. That is why this dataset exists. It was created to fuel predictive maintenance, especially these days with artificial intelligence. With this dataset, we can train an AI model to diagnose the health of a rotating bearing. Even more specifically, we can detect three types of faults: in the inner race, outer race, and metal balls, at different severity levels. This makes it a perfect classification problem. But today, we do not want to discuss the model architecture. We want to purely interrogate the dataset itself. So, how did they create the data? You can download it directly from the CWRU website. Collecting healthy data is easy. You just run the motor. But how do you get faulty data without waiting years for a bearing to break naturally? They cheated, in a good way. They used electrodischarge machining to artificially damage healthy bearings. They created damage on the inner race, the outer race, and the balls. To understand the numbers, we have to understand the rig. They used the 2 horsepower Reliance electric motor. It has two main bearings, one at the drive end, where the motor connects to the load, and one at the fan end. When these bearings spin, they vibrate. Think of it like a baby crying. To a stranger, it is just noise. But to a parent, different cries mean different things. The vibration is the same. It contains hidden information. To capture this crying, they attached accelerometers to the motor housing. They also used a dynamometer to simulate different workloads, and an encoder to measure the average speed and load of the motor. They recorded vibration signals at two frequencies, 12,000 samples per second for mechanical looseness, and 48K to catch those high-frequency ringing sounds that happen in the very early stages of a fault. Now we are ready to generate the healthy, normal baseline data. These data were collected at 48K sampling. We implement the workloads to the motor, measure the motor speed, and store the data. For example, let's see what is inside the final data file. It contains information from both the drive end and fan end bearings. It consists of float values with about 500,000 data points. It also contains the motor speed as a single average value. For generating the fault data, they often added another accelerometer to the base. By creating damage on the components of the ball bearing at different sizes, a massive matrix of possibilities is created. I try to summarize the whole fault data in a table. Let's create this table together. First, we need to know the fault location. Let's start with the drive end bearing. It has three candidate components: the inner race, the metal balls, and the outer race. Normally, most of the load is on the bottom of the outer race, which is the 6 o'clock position. But they also tested the damage on two other positions of the outer race. One is at 3 o'clock, which is orthogonal to the base load, and the other is at 12 o'clock, which is the opposite. Ideally, we have three accelerometers located at the drive end, fan end, and the base. When the fault location is on the fan end, we have the exact same story. The sampling frequency of these accelerometers can be 12K or 48K, and the bearings were tested under 0, 1, 2, and 3 horsepower torque. Finally, we have four different diameter sizes for the fault: 0.007, 0.014, 0.021, and 0.028 inches. They used a specific naming convention to label the data. For example, look at IR007_0. IR stands for inner race. 007 is the fault size, and _0 is the motor load. It seems clever, but it is not perfect. For example, looking at the name alone, you cannot actually tell if it is 12K or 48K sampling. The names look identical. You have to check the folder structure to know for sure. So, we can go on and label experiments for the metal balls and outer race. However, there are several experiments where the data isn't available. We can directly put those away and label the rest. This brings us to the final summary table I showed you earlier. I went through each of them and visualized their information. For example, let's take a look at what is inside the OR021 at 3_2 in the fan end bearing. It stands for outer race with a fault diameter of 0.021 inches, with an orthogonal fault type at 3 o'clock under a load of 2 horsepower. This experiment was only conducted at the 12K sampling frequency. It contains information from the drive end, fan end, and base accelerometers. They are float values and consist of about 120,000 data points. These are the raw vibration data we need. It also contains the motor speed as a single average value, as we expected. Finally, let's judge this dataset. Remember, this data is from the year 2000. The FAIR principles were published in 2016, so there is a huge generational gap here. First, findability. The dataset does not have a digital object identifier at the source. It lives on a university webpage. If the university updates their website, the link breaks. The metadata is just human-readable text on a web page, not attached to the files. And finally, a machine cannot automatically search it. A human must manually cross-reference the files with the website documentation. Second, accessibility. This is actually good. You can download it via standard HTTP links. No login required, no firewalls, no fees. But because the metadata isn't a separate record in a repository, the context for the data can be lost instantly. Third, interoperability. The data is in .mat format. This is standard for engineers using MATLAB, but it is proprietary. It is not as universal as a CSV or JSON file. Although the dataset uses a standard ontology for labeling, after downloading, the clear naming is gone, and users face confusing file names. And lastly, reusability. The website does not clearly state a license, like Creative Commons. It implies academic use, but legally it is ambiguous. On the other hand, the experimental setup is well documented. We know how the data was created. Despite failing the technical checks, this dataset is the community standard. It defines the baseline for the domain. So, what is the verdict? The CWRU dataset is practically fair, but technically unfair. Researchers use it because everyone else uses it. It has become the standard benchmark, not because the data is perfectly formatted, but because of its history. Even today, there are active challenges regarding this dataset, like fixing models that cheat by memorizing the noise patterns, or trying to generalize these results to other machinery. If you are interested, I suggest checking out the Kaggle leaderboards and getting your hands dirty with the data. I hope you enjoyed the video. Thanks for watching.